Hello everyone, welcome to Adson Engineering Academy. It's me, your tutor Adson, and today I'm going to introduce to you a new topic, that is to say pre-stressed concrete. So please, before I continue, do subscribe to my channel, hit the notification bell so that you don't miss any of my video. Whenever I upload a new video, you get notified. So let's dive in and see how to handle the first problem under this topic. Well, so let us have a look at our first problem under this topic of pre-stressed concrete. The question says, a rectangular concrete beam of 100 mm wide and 250 mm thick, spanning over 8 meter, is pre-stressed by a straight cable carrying an effective pre-stressing force P. Let's say it is 250 kilonewton, the way it is given, and it's located at an eccentricity E of 40 millimeter. Now the beam supports a live load of 1.2 kilonewton per meter. The first question says we have to find or calculate the resultant stress distribution for the center of span cross section of the beam, assuming that the density of the concrete is given to be 24 kilonewton per meter cube. And we need also to find the magnitude of the pre-stressing force with an eccentricity of 40 mm, which can balance the stresses due to dead load and live load at the bottom of the section. Let me show you first of all what do we have. So in this question, let me have a summary of what they have given. We have pre-stressing force P has been given to be equals to 250 kilonewton. Then eccentricity E is 40 millimeter. Span L of the beam is 8 meter. Then cross section is given to be, this is 100 by 250. Okay. Then live load or imposed load is 1.2 kilonewton meter. Now from here you can also get the dead load. The density has been given to be 24. You can multiply this by the area. So kilonewton per meters cube. Kilonewton per meters cube is the density of the concrete. So that means multiply with the area in terms of meter. This is going to be 0.1 times 0.25. So when you multiply this, you are going to get 0.6. This is kilonewton per meter dead load. Okay. Now all this I've summarized what I was underlining them what here in the question. So let's have a look at how can we proceed with the calculation. Let's start by getting first of all what we call the maximum moment due to what? Moment due to dead load. Moment due to dead load, I'm starting from this one. Okay, is going to be the dead load, I'm calling it Q L square out of 8. Remember, this is a simply supported beam and we're finding it at the center where it is maximum. So this is going to be 0.6 times span is 8 square, 8, then square it, then divide this by 8. This answer is coming to 4.8 in terms of kilonewton meter. Let us also get maximum moment or bending moment due to live load. Let me call live load as W. So WL squared by 8. So this is going to be, live load is 1.2. Multiply it by L is 8. You have to square it, then divide this by what? 8. So what is this answer? This answer is going to give you 9.6 kilonewton what? Meter. Now, at this point, you need to get what are the stresses that will be developed in this particular beam. The first stress that will come is what we call direct stress. Direct what? Stress. Let me call it DS. And to calculate the direct stress, it is just the force divided by the cross-sectional area. Well, so this is therefore going to be, what is our force? 250. This is in terms of kilonewton. If I want it in terms of newton, then I have to multiply by 10 to power 3. So divide this by cross-sectional area. Cross-sectional area, just cross-section. What is given when you multiply? 100 multiply by 250. So up is newton, down is millimeter square. Okay, so this answer is going to give you 10 in terms of newton per millimeter square. That is our first stress in this one, in this beam. Now, what other stress will be developed? If you look at carefully, there will be what we call a bending stress due to pre-stressing force. Because you have a pre-stressing force, that is what? 250 kilonewton. So let's have a look at how can we calculate a bending stress, BS, that is coming as due to what? Due to pre-stressing force, P. Bending stress coming due to pre-stressing force, P, is given by the formula P E out of Z, where Z is what we call section modulus. We know P, we know E, but we don't know Z. But we have cross section. So let's first find Z. Z, the shortest formula of finding the section modulus is BD cube. No, BD squared, I mean, by 6, not cube. Take note of that. So, well, our B is the width, which has been given to be 100. Then times our D is the depth, which is given to be 250. All this you have to square it and divide by what? By 6. So this answer is coming to 1.04 times 10 raised to the power 6, and this is in mm cube. Okay, now from what we now know, we can go back to this formula and substitute what will be our bending stress due to P. Due to P, it's going to be equals to P, and we know the P value is 250. In Newton it is times 10 raised to power 3. Multiply this by 40, which is our eccentricity E, and divide this by what? Z, which is 1.04 times 10 raised to the power 6. Remember, what is up is Newton, and what is down is in mm cube. So this is Newton, and then eccentricity is millimeter. So that means one of them will cancel. So we remain with the answer in Newton per millimeter square. And our answer is coming to 9.6 Newton per millimeter square. This is our second stress that has been experienced by this beam. But remember, we also have what we call dead load and live load. So how then will their effect be on the what? On the beam. So they will also produce the stresses. And these stresses, we need to see how they are distributed. But since we have already calculated the moment, So from that moment, we can calculate the stresses due to those moments. Remember, we calculated the moment due to dead load and moment due to live load. So let us now calculate the stress due to what? Stress due to dead load. Stress due to dead load. Okay, so this is going to be equals to moment due to dead load divided by section modulus, and this is equals to our value for moment due to dead load is 4.8 kilonewton meter. So this is 4.8 times 10 raised to the power 6 to convert it to Newton millimeter. If I divide this by Z, the value of Z, we also found that it's 1.04 times 10 raised to the power 6. Okay, so meaning that this answer is giving us 4.6 Newton per millimeter square stress. So check the unit, must be correct. Let's have the last part of the stress, which is the stress due to live load. Stress due to live load is moment due to live load divided by section modulus. This is going to be the moment that we found due to live load was 9.6. Multiply this by 10 to the power 6 to put it in Newton millimeter. Okay, so we divide this by 1.04 times 10 raised to the power 6, and this answer is going to be in Newton per millimeter square, and it is coming to 9.23 Newton per millimeter square. These are all the 4 stresses that this beam, particular beam, is experiencing. Now we need to focus on answering our question. Let's have the stress distribution. So according to the stress distribution, this is what you're supposed to have. This is the first one, and the first one is coming due to the stress obtained on the beam that we're calling direct stress. Direct what? Stress, where we calculated in the first part, which is P by A, and we found that the value of that stress was coming to 10. So here is 10, top is also 10, and the sign here is positive. So watch out in this stress distribution, the sign is very important. The second thing is, the second one that we have, down is positive, up is negative, and this is coming is a bending stress due to pre-stressing force P. So the second one is due to pre-stressing force. Pre-stressing what? Force. And we calculated that, we found that it is coming to 9.6 up, 9.6 top and bottom. Okay, then this one, the sign changes. This is minus and this is plus. This is also minus and this is plus, and the overall thing here, the resultant is coming to plus. The stress distribution should be drawn clearly and indicate the values. So we found that the one that we calculated due to dead load was 4.6. So this is 4.6, and due to live load was 9.23. 9.23. So these two is coming as a result of applied load. Okay, applied load. And then these two, they're coming as a result of pre-stressing. So you need to get that clearly. Now let's focus on answering our question. What is the resultant at the top, then the bottom. So let's start with top, the resultant here. So you realize that this is positive 10, again this is minus 9.6, this is positive 4.6, and this is positive 9.23. The answer here is coming to 14.23. So you write it here, 14.23. Bottom is equals to, this is 10 and this one is minus. Before that is plus 9.6, then minus 4.6, then minus 9.23, and this answer is coming to 5.77. So you write here 5.77. We've answered part 1 of the question. Now we need to focus on answering part 2 of the question, and according to the question, part 1 was calculate the resultant stress distribution. Then part 2 is saying find the magnitude of the pre-stressing force with an eccentricity of 40 mm steel, which can balance, take note of this, which can balance the stresses due to dead load and live load at the bottom. At the what? Bottom. So let's have a look at that. At the bottom. Now that means we're going to consider these donor forces, but we are balancing the what? We are finding P. That means we don't know P, but it's balancing dead load and live load. So for that case, we already know the values of dead load and live load, and their what? Their resultant, we already have them. Okay, because the question is we are finding that magnitude P. So let's have a look at it. According to this stress diagram only, you can easily do it. Okay, so I have due to P, here I don't know, direct force P I don't know, out of area, P out of area is 100 by 250, then plus the second one is due to what? The pre-stressing force, which is PE. So this is P also, I don't know, times E is 40, out of Z is 1.04 times 10 raised to the power 6. Now since at the bottom the sign changes, so this is minus, and we already know here this is 4.6 minus this is 9.23. We want to find how it will balance. That means it will be equal to 0, right, for it to balance, or else you have to put the dead load and live load on one side, then these other two on the other side. That's the meaning of balancing. So you have to understand that. Okay, so well, if we take this the other side, we shall have here P by 2500 0, then plus 40P by 1.04 times 10 raised to the power 6 equals to, take this and this the other side, 4.6 plus 9.23. So when you simplify this and divide by what you have on this side, the answer of P is coming to 176 in kilonewton. So please check on this and make sure your answer is coming correctly. So this is the end of this question. Thank you so much for watching this video till the end. If you like the video, if it's helpful, so please like, share, comment, and then above all, still subscribe to my channel so that you always get informed if the new video is uploaded.